Good afternoon, all. I welcome all the dignitaries, respected resource persons, and dear participants on behalf of Department of Physics, Vidya Vikas Mandal Sitaram Govind Patil Arts, Science and Commerce College, Sakri, on this international webinar on a role of advanced materials for optoelectronic devices. Let us move to the second part of this international webinar, and the first session would be conducted by Dr. Nishadji Deshpande. So for his introduction, I would like to invite Dr. Anup More for the introduction of our honorable resource person, Dr. Nishadji Deshpande. Over to you, More sir.
Okay, sir. Thank you, sir. Good afternoon, all of you. I am here to introduce next speaker, Dr. Nishad G. Deshpande. Currently, he is working in Advanced Material Science and Engineering Department of Sungkyuan University, Suwon, South Korea, as a research professor. He has almost 1 decade of experience of postdoctoral researcher in different Asian countries. He also have experience of DST Inspire faculty in the Department of Physics, Shivaji University, Kolhapur. His research interest is nanomagnetism, spintronics, magnocalorics, solar water splitting, photocatalysis, and gas sensing. There are several awards in his account, but due to time limit, I will read only selected. The first, Brainpool Invited Scientist in National Research Foundation, Government of Korea, and Young Research Associate Fellow, Maharashtra Academy of Sciences, Pune, Maharashtra. He also have lots of best posters and papers presentation in national and international conferences. In his account, more than 70 plus research publications are in national and international peer-reviewed journals. He also have more than 7 book and book chapters. Recently, he also filed 2 Korean patents. He also completed 4 major research projects of total cost around 44 lakh. Today, he delivered talk on designing smart materials for highly efficient optoelectronic devices. Now, I would like to request Dr. Nishad Deshpande to deliver his lecture. Over to Nishad Deshpande, sir.
Yes, thank you. Yeah, can you see me? I mean, see my slides, and can you hear me?
So your slide is visible.
Okay.
You are audible also, sir. So
okay, thank you very much, sir. Thank you very much. So thank you for a nice introduction, Dr. Anup. And I firstly would like to appreciate SG Patil College, Sakri, especially efforts of Professor R.R. Ahire sir, Professor Sonone sir, Professor Sachin Nandre sir, Professor Sudham Chavan sir, Professor Jnaneshwar Chavan sir, Dr. Anup More sir, and well, all other team members of SG Patil College who have taken this initiative to organize this one-day international virtual conference on optoelectronic devices. Actually, I would say this should be really an inspiration to all of the nearby colleges, considering the present COVID crisis that we all are facing. Also, in the coming years, the academics are going to change in such a way that we are going to connect through these ICT techniques. So this would be a good start for now, from now on. So I would like to really see forward for a very nice conference. And also, I feel like in the morning session, we came across different speakers, in particular, Professor Fase sir, Professor Ramphal Sharma sir, Professor Aris Mane sir, who have given a very nice talk regarding the trends of various optoelectronic devices, then batteries, and then supercapacitors, and how these techniques or technologies are going to change in the near future. So this is really inspiring in talks by them. And today I would be focusing on a topic which says like designing smart materials for highly efficient optoelectronic devices. So particularly I will be talking about the multi-purpose optoelectronic devices using in photovoltaic technologies extended to chemical reactions, in particularly the PEC cells. Else. Right now I'm working as a research professor at Sungukwan University, Suwon, South Korea. So here also we are facing the COVID crisis, but rather Korean government has controlled it quite well. However, all the lectures are online, and we are all doing it like maintaining the scenarios by giving presentations online, and also interacting with students through online techniques or having meetings. So this is a good platform again, and I would like to come to the contents of my topic here. So here is what I would like to cover in my topic. First one is the overview of the optoelectronic materials. Secondly, I will talk about the materials, lengths and scales. So on the length and scale, how these materials are going to behave and how they are going to change the properties. So that is one of the important aspects I would like to focus on. Not only that, I would like to go to key parameters, like what are the key parameters that governs the optoelectronic devices. Secondly, I will come to a simple understanding of the PEC PEC cell for water or splitting, and how this water splitting is being utilized in energy generations, like H2 fuels. And I will come to my topics like controlled nanostructure bismuth vanadate, and then antimony selenides, and why we are using these materials for particularly for PC water splitting, and also for the photocatalytic dye degradation mechanisms to resolve the wastewater treatments. And lastly, we'd like to conclude with a summary. So here you can see on this slide, like I have just tried to give a very brief idea about what is optoelectronics, or what are the optoelectronic devices. It's nothing but coupling between in the optical as well as the electronics. So optical in the sense that you are utilizing the photons, and then you are generating the electrons and whole pairs, and thereby you are utilizing these techniques to develop different kinds of devices. In particular, you can see here the solar cell is a well-known example of this optoelectronic device, where light is being utilized to generate electron hole pairs, which are separated externally through external biases. And then these separated electrons and holes move through the external circuits to which can be utilized for different kinds of applications, or which can be utilized in different kinds of devices. Yes. So what are the various optoelectronic devices? So you can see, like particularly you can and go through either charge, I mean utilizing of charges, and to make photons, or to generate light, or the vice versa, like using of photons and making charges, different kinds of charges. So particularly this is governed by the semiconductor materials, wherein, and not only the semiconductor materials, but it is governed by, actually I would call the band gap, which will define the material properties, as well as it will define what kind of technologies can be developed through this. And you can see that using charge, you can and generate photons, which is nothing but the examples of light emitting diodes, or laser diodes, and the vice versa, wherein you are using utilizing photons to generate charges, is nothing but the solar cells, PC cells, or photosensors. So particularly our lab is focusing on two important aspects of PC cells as well as photosensors. So I will be focusing more on today on the PC cells here. here you can see that these optoelectronic devices are not really confined to only these is topics, but rather now they are being expanded because of the interdisciplinary nature of the research. You can see that in organic semiconductors, where organic LED devices are being in developed. So this is not extended to just inorganic materials, but rather organic materials are being also utilized these days. You can see like ionics, protonics, we are well known with the optical sensors, and then now it is combined to the nano medicines as well as nano bioelectronics, wherein, and this is the current need, because we are as we are all aware about the corona crisis. You need to be having devices that are utilizing this is nano as well as bio and then electronics to actually test the samples of these corona patients. So which is been in quite fastly and rapidly been developed these days in various countries, is globally as well as in India also. You know, so these photonic or you can say like the optoelectronic devices are mainly having a very large aspects of research these days, and particularly what we are trying to see is the clean energy. So this is what we are trying to deal with, to understand on how we can generate clean energies using optoelectronic devices. So if we try to see a global scenario of designing of these devices that involves optoelectronics as well as PEZ mechanisms. So what I can see here is like this is taken from the motor intelligence source, and you can see that at almost the South America or the Africa continent is well versed, and the economic growth for 19 to 24 will be very high. Not only that, you can see that the European countries or the Asian continents, and as well as the Australian and the North American continents will have a very sudden increase in the opto electronic market growth. India also will be facing this same scenario soon. So if we see that the global trend is towards what? The development in materials. You can see that this is on the time scale I'm talking. So it was that the time on the time scale earlier, the materials else will started to be developed. Now not just the materials, there is innovation in different kinds of materials. So the same materials you can be innovated in different kinds of forms to actually adjust its prerequisite properties for different kinds of devices that can be utilized. Not only that, now these materials are being going into the nanoscale or the quantum phenomena, where you actually require to make small devices, or the miniaturization can be possible. And you can see here like what are the actual global trends these days of research. It is nothing but the white LED, which was given which was developed recently and was awarded with the Nobel Prize. Then you have displays, you have laser machinings, you have smart wearable devices. So this is also becoming a very important topic these days, wherein you can and see the nanotribiology generators are being utilized to generate energies is through utilizing the piezoelectric phenomena. Not only that, you have an image sensors. This will also become a very important research topic because concerning this kind of crisis, COVID crisis, image sensors will be very important in near futures now. Not only that, optic couplers communication is already been in focus now due to ICTs and all these optical fiber communications, and which utilizes again the optoelectronic component. So this is going to be leading topics these days, and the most important coming topic, almost like you can see that the General Motors and Chryslers are utilizing this H2 production, and they have actually developed a car which is utilizing this kind of hydrogen fuels. So this is also a very good technology being utilized these days using optoelectronic devices. Here, what I would like to focus on is like what are the key parameters that are going to govern the optoelectronic devices. So what I find is the most key parameter is nothing but the band gap here. So it defines like how your material is behaving. Either it is a metal, it is an insulator, or it is an semiconductor. So this is well defined by this is band gaps. Not only that, you can see like I have shown here like two different kinds of band gap. One is an direct band gap, the other one is an indirect band gap. So ultimately this is property of band gap, either it is an indirect or direct, it will going to define your actual optoelectronic device properties. Here you can see that LEDs which utilizes is most of the direct band gap materials else are very important and in developing in different optoelectronic devices. There are some phonon assisted also devices, but rather we are not going to focus on that. At mostly we will be focused on the optoelectronic devices. You can see that you can make different kinds of quantum wells, else wherein actually the electrons can be trapped into the quantum well, and you can and produce an amplification of light, thereby producing a coherent laser system in using optoelectronic devices. Let me come to the lens scales now. So what is important? Usually I talk upon this very much because we are moving towards the miniaturization, where atoms and atomic or nano structures are becoming an essential part of our studies. So you can see like when you go on top to bottom nanostructures, actually at this lens scales, most of the properties are going to change. Now when I was talking about band gap, so I will come to the best example of this band gap, and then at the lens scale how it is going to change. You can see from this cartoon here, where I have shown like this is an valence band and the conduction band, and I have shown here that single atom nanoparticles and bulk materials. So this is a very simple and easy way to understand, like if you have a bulk material, so what it means is that you are having numerous atoms or molecules together, which are having nearly similar kind of energy levels or adjacent energy levels, which are being merged together. And you can see that the valence and conduction bands are so consecutively spaced, is that the band gap is quite smaller in this case. In case of nanoscale, when you can see that the atoms are going to confine now, so that means you are having finite numbers of atoms, and therefore the overlapping or the energy level bandwidths will start to be narrowing, in the sense that you can see the band gap will be widening. So that means that if when you're going to the nanoparticle region from the bulk, you will see that there will be changes in the band gaps. Yeah, as well as if you are having a single atom, now what is there is nothing but a discrete energy level, and you are having a more wider kind of band levels. So this means like the important property of a material that is a band gap can be easily controlled when you're going through the lens scales. Not only that, if you see that if you're having a widening band gap, that means the electrical properties are changing. You are having a low conducting material in that case. Also there will be a shift from say red to blue. So actually you are moving to the blue or the ultraviolet regions. So you can see on this lens scale, this is a bulk level, and you're moving to the atomic level. What you see is nothing but there is a shift from the band structures. So that means like the controlling parameter is very important when you're going from bulk to nanoscales. Here I would like to show you like the current focus. What we are actually trying to do is, already like last slide we talk about optical and electronic coupling. Now what we are doing is, with this optoelectronic coupling, we are trying to couple the chemical reactions, in particularly the redox reactions. So that means like using optical, electronic, and now chemical reactions, we are developing devices for the near future fuel technologies is and that's what is the current talk about, and I will be focusing on this. Now the you can see that this is well known, like the solar energy is quite immense and it is falling on the earth's surface. So this means that the radiation is almost like 120,000 terawatts, which is quite huge, and the energy demand is continuously growing in day by day, considering the density of surface volume towards the utilization of energy. So that means the global consumption will approximately increase is to, or it will be double to almost 30 terawatts in 2050. So this means consumption of energy will be continuously increasing. I would rather say it will be steeply increasing and we will be falling short with different kinds of the fuels which are utilizing today. So that means we need an alternative, and therefore this solar energy need to be bestly utilized for different kinds of devices where we can actually generate energies from the solar energy. So you can see here that this solar energy can actually be utilized in different kinds of capturing, wherein like these trees and plants, they use these solar cells and then they develop the chemicals which are useful for their growth. Not only that, the microorganisms, organic dyes, semiconductors, they utilize this. So this is an capturing phenomena. Secondly, conversion of this is captured phenomena as or the ingredients into different forms. This is utilized by most photosynthesis again, and then solar cells, solar fuels else. And lastly, there is a storage concept like hydrogen storage, biofuel storage. So particularly what we are doing is we are utilizing this concept of capturing, conversion, and storage for or preparing our optoelectronic devices. Particularly what I will like to see is why hydrogen is becoming in the ultimate fuel for next or future generation. And this is why, because as the fossil fuels that currently we are using, like coals else, or you can say like diesels, and these are going to extinguish in near future. Getting energy from these sources will be rather very difficult. So we need to find alternate, and this hydrogen technology is becoming the next future generation and fuel for us. So we need to utilize now all these forms of photons or optical, combining with the electronics and then combining with the chemical reactions to make hydrogen generations for our fuel technologies. Secondly, it is a clean source, so that means no greenhouse effects or global warming issues will be arising because of this. Is and the important point is how these hydrogen can be produced. So probably there are so many ways in which you can produce that. Most important or most utilized cell is nothing but the electrolysis but rather what we will focus is just the photocatalytic water splitting. So I'll come to this water splitting. So what is a water splitting? Like, it is a chemical reaction, and it is chemical reaction in water, where the water is being splitted into oxygen and hydrogen. So this is the basic and simple way. Now how we are going to achieve is nothing but using photon, electron, and chemical reactions. So this water splitting can be easily achieved with this. I'll come to a simple understanding like how we are going to do this. And before that, we would like to see like why PEC water splitting is becoming important. So this is becoming important for the reasons like this particularly was inspired through the photosynthesis mechanism from our plants. The nature is giving us so many things to understand, and we need to understand the simple mechanisms that nature has been given to us, and convert into artificial devices is where we can utilize is the same concepts, but for our benefits of mankind in forms of energy and many other ways. So here you can see that this H2 production, in although this is H2 production is a simple step, but rather splitting the oxygen from the hydrogen is a very sluggish thermodynamic reactions, which involves almost 4 steps, and you need to overcome different steps with different gives energy. And this becomes a very difficult aspects. So splitting of water is also not a simple mechanism, but with utilization of optoelectronic devices, you can do this very well and very easily. So you can see like studying this is photocells, we can actually go and make different devices using which can be utilizing or separating the water or and into hydrogen and oxygen. So here you can see like probably this might be the most easiest way to understand and the water splitting using in the semiconductor materials. So particularly this is an photoanode which is active for the utilization of light. This is the counter electrode, and now photoanode usually it generates the oxygen, while the counter which is an photocathode which generates the hydrogen. So you can see like the photons which moves towards the cathode photo anode are being absorbed now. Oh, and then what happens is you can see with the absorption of this light, electron and hole pairs are generated. Now the electrons move through the external circuit and they comes to the counter electrode here. So this means the circuit or the applied voltage is separating the electrons now. Now these electrons will be utilized in separating the H2O, wherein these electrons will be utilized to generate OH minus radicals now. Now these radicals are certainly they are moving or they are conducted through this is water and they move towards the photoanode where they combine with the holes, and you can see that the reaction is again an H2O formation with O2 coming out. So that means like you can actually generate at the hydrogen and oxygen, and at the counterpart you can see H2 is generated because the electrons are moving or OH minus is moving here. So this means that this reaction and is combined with the light as well as the charges is, and as well as the utilization of chemical reactions here to separate the H2O. Now at what voltage actually this occurs is 1.23 volts, where this water splitting takes place, and actually you can have H2 production from H2O or oxygen production on in this is particularly a particular cell. Yeah. So what we are utilizing here is a bismuth vanadate. Why we are trying to understand this bismuth vanadate is because it is having a low band gap, almost like 2.4 electron volts. It is really a less corrosive or photocorrosive material. So for studying the commercialization aspects, you need a material which should be withstanding in for a longer time without having any deterioration in the properties. So this is very important aspect of this bismuth vanadate. Not only that, it is cheap, non-toxic, and abundantly available. So that means making of bismuth vanadate is quite easier, and for commercial purpose also very economical. It has a very perfect band edge positions for or splitting the water to produce H2 as well as oxygen. So that means it is very important material. And secondly, bismuth vanadate, which belongs to the ternary bismuth oxide, where BIM and O structure or the bond structure is present, which makes it more unique because now this crystal structure has different kinds of forms, and probably you can actually deal or deal with the facets, different kinds of facets of this bismuth vanadate. Not only that, it has an effective electron hole mass, which is quite exciting as compared to TiO2 semiconductors. So that's why we are utilizing bismuth vanadate here in our study. So I'll come to the basic point of this study now. Now, what we are doing is we are designing these nanostructures of bismuth vanadate. Here, I have shown like we already did nano powders, we did thin films, which are an epitaxial thin films, and then what we did is we tried to combine these two techniques into one, and how we can utilize the facets now. So here you can see like the bismuth vanadate has multifacet. It is a polyhedra structures. Each facet is very active in bismuth vanadate. And not only that, if you go on making nanostructures, then actually these facets you can control, and you can make these facets like a flat surface or a broad surface where these facets are very active. And in particularly if you want to see like the 110 facet, this facet or this facet here shown, which is very effective for oxidation reactions. Not only that, if you see the 010 facet, it is very good for reduction reactions. So that means now with controlling these facets, we can actually control the reaction properties of this PEC cells. So what we did is we combined now this structure, and we tried to see like if we have two different kinds of facets involving in one structure, what it will happen. So what we did is we tried a simple process test in which we use simple spin coating methods, and we achieved the nanoparticles, and then we control the facets in such a way that we can actually have two different facets, and we studied the PEC mechanism, water splitting mechanism of this. Here, this is our experimental details where you can see like this is a simple bismuth vanadate precursors were mixed into nitric acid, and then they were mixed thoroughly and spin coated on FTO substrates. And after annealing, you can see that the structural properties are shown here. So we changed the bismuth and vanadate concentrations, and what you can see is the facet actually 002 is changing towards 111. So that means you can now control these facets with just changing the concentrations. Here, the morphology, you can see like the nanoparticles we formed had polyhedra-like structures, but rather when we change the concentration, we see that the nucleation started, and this nucleation is favoring the 020 facets. So you can see most of the polyhedra structures as well as the facets which were shown earlier. And when we change the concentration more at a higher end, what we can see is that a rod kind of structures is growing up now. So the nucleation is slowly making rod kind of structures where the 110 facet is more effective now. So this means a combined structure is achieved where 1110 is more active compared to 020 facet. So we made this similar kind of cell like what last time I have shown, combining in the photoanode of bismuth vanadate and counter electrode as platinum, and we made this cell, and what we can see is that when in the dark there is no current generation, but rather when we applied the light, what we can see is the current starts to grow up now. Now, when the bismuth concentration increases, what we see is that the current continuously increases. So at the facet structure of combined facet structure of 010 and 020, we can see that the current is having in a I mean very high current is evolved for these structures. And what makes this structure interesting is we try to understand the eta transfer. Now this eta transfer, it is the transfer of charges from the semiconductors towards the electrolyte. So this is the efficiency with which the charges are getting transferred. So you can see that the concentration of 3, like bismuth vanadate ratio 3, has almost a very high eta transfer of nearly 48%, and compared to the other concentrations. And as well as we try to understand the eta transport. Now eta transport is nothing the within in electron hole pair generation. I mean within the semiconductor electron hole pair generations. So you can see at this point also it is having a very high eta transport efficiency of transport. So that means like this facet structure is very useful in increasing the current values, and thereby it can be very essentially be utilized in separating the oxygen from hydrogen in the PC cell. Not only that, what we did is now at the same conditions, we just inputted some methylene blue into this reaction, and what we did is just by FTO, there is no change in the absorption, and but rather when we utilize our structures, what we can see is that almost like at 300 minutes there is 85, 91 and 96. So this means almost 96% of degradation taking place with the combined facet structure of bismuth vanadate. We try to see the utility of, or we can see the stability. So almost like 9 cycles it is quite stable. A very slight change is seen after 9 cycles. So this means that the photocorrosive properties of this material is also very good, and one can utilize this structure not only for the water splitting, but now for the water treatment also, where the dye degradation can be easily seen. We also tried to see in putting in Congo red dye. So earlier we tried for a methylene blue dye here, and now we tried for an Congo red dye. So what you can see that now this is more fast reaction, and in within 90 minutes you can achieve 86% of your dye degradation. So this means like this facet is more active towards the Congo red dye. And we try to understand using the contact angle, because this actually gives us the active surface is surface studies using understanding the contact angles, like it is in hydrophilic or hydrophilic surfaces. So what we can see is, with respect to the Congo red dye on the bismuth vanadate structure, we can achieve a very low, almost like 34 to 36 degrees of angle, which means that this is very highly intercalating in these dyes with respect to the surfaces of the bismuth vanadate nanostructure. So this means like these is dyes will be rather fastly degraded on these surfaces. So this is what our dual utility device is all about. This is what we have been proposed in the mechanism, like utilizing the same structures of bismuth vanadate, which is having a very high active facets of oxidative and reductive reactions. One can use this cell for water splitting, where we are applying an external bias and also the light to separate the electrons, and we can actually achieve the oxygen evolution, as well as the change in the or the splitting of hydrogen. And not only that, the same structure, if inputted with some dyes, what we can see is we actually can degrade the dyes now, but there is no external bias now. So this means like this material is very much utilized for both, wherein you can use the optoelectronic mechanisms, or you can just use the optical mechanisms here. So this makes it's a really versatile material, which can be used for sustainable energy production, as well as wastewater treatments. Now this is a commercial aspect of our study. So this paper deals with antimony selenide. So we tried for another material. Now this antimony selenide has a very low band gap, almost very lower than bismuth vanadate. And what we can do is, now again we try to control the facets here. You can see like the 0k0 surface, which is having covalent bonding along this direction, and it is having or you can say that the facet H0L or H00 having in the bonding structure, like van der Waals bonding structure along this direction. So what we can see is that with change in the facet structure, you can actually control the hydrophilicity or hydrophobicity. So our main purpose was to make a bifunctional membrane, which can utilize for both oil separation as well as the photo degradation of the dyes. So therefore, we developed this material on a platinum mesh, and you can see that these structures are having in nanorod structures, which are having both surfaces now. So we combine into this device. Now we made this is a simple device where we utilize this is mesh on which we have grown the antimony selenide, and we inputted here. And what we did is, we actually put water combined with oil, and for just demarcation purpose, we have shown some color added, like hexane was added with blue color, and water was added with methylene orange. And when we input into this, what we can see is that the oil part is coming out, while the water part or the methylene orange part is confined now at the upper stage. When we irradiated this same system, what we can see is now the methylene orange, which is containing in the water, is degraded, and you can see that degradation is here shown. like almost like within in 30 minutes or so, we can see a clear degradation of this is methylene orange. So that means the utility of achieving both bifunctional oil separation as well as photodegradation can be done using this simple material. And this is where the optoelectronic devices are being useful now. Now, for simple understanding, I would like to show this video. I hope this works. Yeah. So you can see this simple video. Now, this is our apparatus here. We are inputting the oil. We are inputting the water, and which is mixed with methylene orange. Now we are inputting in the oil with some hexane, and now we are just inputting this solution into our this tube. Now the mesh structure and the antimony selenide is here. What you can see is when we input, slowly the oil part is coming out now, but rather the water part is confined here. So this clearly shows like the hydrophobic surface which we have developed using the facet structures can be very well utilized here. Yeah. So lastly, what I would like to conclude is that the current focus is detected towards the energy research, and hence the optoelectronic devices are becoming very necessary. With the new dimensions of utilizing these optoelectronics with the chemical reactions, one can develop devices that are useful for hydrogen productions or hydrogen fuels. Smart structures of bismuth vanillate and timisolinide are developed, and which are developed for both sustainable energy as well as wastewater treatments. And controlling these nanostructures are essential for developing advanced devices for near future in electronic sensors, energy treatment, wastewater treatments, and many more. So thank you very much for having a very patient listening of my talk, and I would be rather happy to have some questions on this topic. Yeah, thank you very much, sir. I hope all are. So hello, hello, hello.
Thank you, sir.
Hello.
Thank you very much.
Yeah,
Uh,
thank you, sir.
Sir, there are some selected questions from the chat box we have
Yeah, yeah,
received
yeah.
in
Yeah, please, please.
YouTube channel. Just let me read the first question. What way the optoelectronic devices can useful to the common man, and it is asked by Prakash Wow.
Yeah, um, it's quite a wide question and very nice question by Prakash sir. Actually, I have already focused on these parts, like how these optoelectronic devices are being utilized. So you can see, like mostly the basic example I have given is a solar cell example. So this solar cell example is very much important for current scenario where energy crises are becoming very important in daily life. So I feel like these optoelectronic devices is can be utilized not only for solar cells. It can be like this slide shows, like almost it can be utilized in almost communication, solar cells, hydrogen production, optical couplers, or imaging sensors, and so many aspects. So I hope my answer is this one, like how it can be utilized for the human mankind or the society.
Thank you, sir. Sir, there is another question. What are the differences between in bulk and nanostructural materials of
Yeah.
optoelectronic properties? And it is asked by Hiralal Pawar. So, would you please,
Yeah.
sir?
Yeah. So actually, this slide was which was focusing on lens scales. So you can see like here, because there are so many aspects, I would like to only focus on the band gap aspect of these materials. So you can see like when you go from the bulk to the nanomaterials, the confinement of atoms or finite numbers of atoms makes the energy band levels quite widen, and therefore you can see that the band gap changes. So this means like when you are changing the band gap, that means the electronic properties are also going to change, because the band gap defines like you are having a higher band gap, that means you are going and insulating in kind of materials. If you are having a lower band gap or there is these how can say modulation of band gap, then you can see like the valence band or the conduction band which are overlapped to each other, then that means you are going to the metallic structures. So this is how like with change in the length scales from bulk to nanometers, you can see that there will be a vast change in the material properties. So just I have focused here band gap because we are talking about optoelectronic properties. I would like to say like this is most important point here, like how the length scale will change the material properties.
Thank you, sir.
Yeah.
And the last question is from Miss Spandana. And the question is, what is the concentration of dye solution?
Yeah, right. Oh, very good question. Yeah, actually this dye solution concentration is almost like 20 mg per liter.
Thank you, sir.
So
I
yeah, which
hope.
is a standard concentration being utilized by almost all peoples.
Okay,
So that
okay.
is the same what we are utilizing.
Okay, I hope the uh, scholars who have asked these questions would have got their answers. Now let
Yeah,
me
hopefully.
conclude. Thank you, Dr. Nishadji, for having a very explorative deliberations, and you have just focused trends in designing devices, various key parameters governing optoelectronic devices, and the changes have been taken in them. Also, you also have explored current research scenario in this field, and particularly you have focused the solar energy field. Your brief explanation with on various technological methods how to produce hydrogen and water splitting, that is also very interesting. You also given uh, your information regarding various designs of smart structures and various applications. I would like to thank on behalf of organizing committee and Sitaram Govind Patil Arts, Commerce and Science College, Sakri. Thank you very
Yes,
much,
sir.
sir.
Thank you very much, sir, for giving me this opportunity.
Thank
And thank you very much. And I hope all are safe and stay safe
you. Yes.
in
Take care, sir.
Corona crisis. Thank you. Thank you very much.
Thank you, sir. Thank you, sir. Thank you. Now, dear friends, I would like to shift the second session of the second part of this international webinar. And for this, we have the eminent resource person from Australia, Dr. Prashantji Sonar. And for that, I would like to request to Dr. Deepak Nagrali to introduce Dr. Sonar. Over to you, Nagrali sir.
Uh, Thank you, Johan sir. Uh, equal. Okay, thank you, Johan sir. I am here to welcome our next eminent speaker.
So here we are. Myself, Dr. Deepak Nagare, Department of Chemistry. I will take this opportunity to welcome uh, our this session's eminent speaker, that is the Dr. Prashant Sonar. To introducing biodata of Dr. Prashant Sonar. It is not, when I going through this biodata, it is not just biodata. It is his overall journey, how he traveled from his uh, uh, college to the today his positions. So I'm starting his biodata. He's recently working as an associate professor at Queensland University of Technology in Australia, and his qualification, if you go through his qualification, we will like to add one sentence here. He's our alumni, and his bachelor degree is from our college. This one is the most appreciable thing here. So he has a bachelor degree from our college. He has a master degree in polymer chemistry from North Maharashtra University, Jalgaon. And after that, he did his PhD from Germany. After doing his PhD, he joined a postdoctorate fellow, and his journey is going far towards the expertise in this chemistry and physical sciences. So if you're going through his biodata, I come up few points I want to mention here. He started his journey of this research by PA2 position in the National Chemical Laboratory. After doing the project fellow, he did his PDF in Berlin, Germany. After doing PhD PDF, he joined as a research engineer. After research engineer, is going proceed further for the senior research engineer. After this, he joined as a research scientist, and ultimately at Queensland University, he is now working as associate professor. From a rural place to the university like in Australia, Queensland University, the journey is quite inspirational for all of our rural students also. That's why it is our eminent alumni, as I said earlier. If you go through a short his awards or his professional activities, I have summarize some points because the biodata is very long, and I have to mention a very brief, very important point. So he has very different awards from different countries also, from India, Australia, Japan, Singapore, and is a PDF in Switzerland is also got different types of awards. And if you go through his professional activities, he's a editor, editorial board member of various journals, reputed journals like ACS, RACs, or JACS, different advanced material science journals. And he also reviewer for the different funding proposal agencies of different countries like USA, Singapore, Hong Kong, Europe, Canada also. It's his overall research output, if you conclude, he has published up to the 155 research papers. He has a H index 40, and total citation is a 6,300. He has delivered more than 80 talks in different conferences and seminars. That is his short biodata of from this biodata, we can conclude the quality of Dr. Sonar has gained his entire journey. So I'm again on the behalf of the organizing committee, I welcome you, and I'm requesting you to start your presentation. Thank you. Over to you, Chavan sir.
Okay, I hope everyone can hear me. Thanks first of all to my senior college, H.G. Patil, which I'm carrying that kind of legacy, and I have learned a lot of interesting chemistry and physics from all my gurus and teachers who are in the audience. I'm really grateful for giving me this opportunity to Sudham and Professor Aire sir, particularly for this wonderful conference. I'm delighted that H.G. Patil is putting so much great initiative during this COVID situation to bring some of the world-class researcher and utilize this platform to give the knowledge to our students as well as academics about the cutting-edge research activity. So I'm just going to share my screen and then I'll start my presentation. I hope you can see the slides now. Sudham?
Yes, sir. Your PPT is visible.
Yes.
Okay, very good.
Yes. Carry
All
on.
good.
Carry on.
So I'm just starting. Okay. So today I'm going to talk about particularly advanced functional material for electronics, display, and energy. So first, I'll just wanted to show exactly about Australia and where the location is. I'm going to give some sort of a brief introduction about our university, and then later on I will start the scientific talk. So Australia is some sort of a like eastern part of the world, and if you look, particularly Australia is a very big country. If we travel from our city towards India, half of the time plane is on Australian territory. So you can imagine how a big as a size of this country is. And looking at this, Brisbane, particularly, which is located again eastern part, which is a very nice area, very close to the Pacific Ocean. And the best part of the Australia, we get 360 days of sunlight, and that's what we called as a golden sunshine coast or gold coast. These are the very famous places close to Brisbane. And looking at the particularly our Brisbane city as well as our university, our campus is located in a two different part of the city. One is a Garden Point and another is a Kelvin Grove. So between these two campuses, we do have a shuttle bus service. And this is a wonderful Brisbane River. So having an aerial view of that Brisbane city, most of our research activity happens in this Garden Point campus where my laboratory and research students are located. And we do have a botanical garden just nearby and Brisbane River. So sometime if research is not progressing well or we get a little frustrated, we can have some jogging near to the this side, and I mean we can really pacify some of our unsuccessful stuff. So it's really a wonderful city. So just I wanted to start first, like why organic electronics? If looking at about the organic electronics, it is a 330 billion market. It's a very big kind of activity, research activity, and by 2027 it will reach up to that value. And if you would have been noticed that currently OLED TVs are already in market, like Samsung and LG has put up the organic light emitting dart based displays in mobile phones, their current Samsung models, as well as in their display TVs. And it is really kind of moving towards automobile and smart kind of a solid state lighting, white light emissions, and smart walls. So organic electronics can be collectively applicable for various applications, including lighting, smart fabrics, solar cell, batteries, actuators, biosensors, lab on chip, transistors, and smart tags, and signage and all. And particularly these three Nobel Prize winner, Alan McDermid and Alan Heger and Shirakawa, those people who discovered the conducting polymer, they got the Nobel Prize in 2000. And I mean, a really remarkable journey from 1977, the first conducting polymer was invented in Shirakawa's lab in Japan. And it took almost more than 25 years to come a real product in the market by LG or Samsung. So this clearly indicates that from lab or concept to the real product for the humankind benefit takes really a long way. And that's what evolution of science and what we scientists or what we academics do, trying to explore new materials and new functionality. So looking at the organic and printed electronic devices, particularly displays, which the benefit of compared to the inorganic rigid silicon semiconductor, and that's what we called as a Silicon Valley, because we make the all microprocessors and all those transistor devices for today's computer chips using silicon as a rigid material. The beauty of organic compared to the silicon is that we can really tune the optoelectronic properties of organic by tuning the band gap. And another important aspect, in case of a carbon-based material, we can make the functional inks. It means that we can solution processable to the large area devices. So we can print them, we can make roll-to-roll printing, and we can make a flexible solar panels like some sort of, the big rolls, or might be we can have tomorrow the display TVs, they can be like a calendar. We can just roll up and roll down. And again, I mean, it is not far now. Samsung has already their flexible base new model of mobile phone has already launched in the market. So I think looking at this carbon-based material, the functionality where we can have a soft functionality which we can introduce, and we can really tune band gap from the high band gap to the low band gap. Whereas in case of silicon, which is a rigid material, the processing cost is quite high. So it is a bit hard to process them on a large area scale devices. And I think the cost is really the main game changer. Again, using carbon-based material, we can make a plastic electronics. If suppose tomorrow we want to make a flexible TVs, which can be like a calendar, we should have a transistor, which is a backplane to run the display devices of OLED, using the transistor as a circuitry, as a background kind of circuit. And until unless we don't have this flexible circuit, it is hard to make the flexible displays. So that's what organic thin film transistor plays an important role. And again, organic solar cell, which is a pretty exciting research area where we can harvest the solar energy from the sun naturally, and we can get a maximum electricity. And as you know that currently world is facing, I mean, the fossil fuel has limitations, and we should have this new renewable energy sources to kind of collect the energy from those, cheap sources or non-conventional sources to get the more energy. And looking at the carbon-based material, which we can design and synthesize in the lab, and you can see they can be like a carbon nanotubes or buckyballs, or they can be a polythiophene or some type of a dyes and pigments. So looking at my particular group in Australia, my team here develops the molecular material as a functional organic electronic devices to are flexible and printable. And this is some sort of a snapshot. Actually, we do a lot of work on dyes and pigments, which is my passion, because those are colorful, cheap material, which we can functionalize by doing some chemistry on it. And then we can reduce the pi stacking distance. We can make a different kind of light emitting material as well out of it. And it can be utilized it as a transistor devices, or might be an organic solar cell, or it could be useful for OLED type of devices. And looking at like transistor and OPV and OLED, I will give a little bit insight about how those devices are fabricated later on. But it is like OLED and OPV is some sort of a vice versa. You convert light energy to the electricity in OPV devices, where in OLED devices, you are putting holes and electrons together, creating the photons, and you're getting light out of it. And the photon color is depending on the band gap of the material, and you can tune really red, blue, green, and you can make a combination to make a white light emission for solid state lighting. Whereas in organic, we harvest the photons and we get the electrons out. Whereas a transistor is a 3-terminal device, which is like a switch, which we can control the current between source and drain just by applying the gate voltage. And I'll explain you that one much more in detail. But in my group, I'm very ambitious to expand this activity towards a lot of different exciting new type of devices. So this is my Australian lab, where we do have a synthesis laboratory with a very well equipped fume hoods, where we do the functional material synthesis, and we do also have a device lab where we can do the spin coating. We can deposit the metal electrodes, type of vacuum depositions, and those are the 2 glow boxes where we can have a complete device fabrication on a small scale. And if you wanted to go for the large scale, we do have recently got the printing, which we can go at least quite a good size of the device. But still, like to go to the A4 size paper, still we require facilities by Australian National Lab called as a CSRO, where we take the help, and then we get the bigger devices made out of that. So looking at the organic semiconductor electronics as a current and a future paradigm, like some sort of a scenario, you can see the foldable smartphones are there. Apple has their smartwatches using the OLED display. Stretchable electronics is really upcoming field, where if you wanted to have these electronic tattoos on your body, if you're running and you want to monitor some sensing parameters, those can be embedded, or those can be putting on your body. And that's what the stretchability is required, because our bodies keep on moving, and the performance of devices should not change upon the stretching of body. And that's what this mechanical aspect is required. Biodegradable electronics is another exciting field, because electronic waste is the biggest challenge. And I mean, as you see in currently, once the computers are outdated, all those circuits and chips, and it's very hard to kind of I mean, still people can take out metals and all, but again, the recycling and then environmental aspect. So that's what we have to come up with, some biodegradable plastic where we can put these transistors, or maybe make the biodegradable materials which can be feasible to the biological body, and some of the devices can insert it inside even the body and can be utilized for brain mapping or I mean other organ mappings. And then solid state lighting, OLED, that's like white emission, which we want. Flexible solar cell is another one. Rollable display, then the self-healing sensors. Some of the materials, upon you put up a mechanical damage, they have ability to kind of self-repair by themselves. It is some sort of feels Hollywood type of movie, how these type of things can happen. But I mean, it is really a human machine type of interface, and there are a lot of interesting aspects are happening. Like flexible circuits, then the smart contact lenses, and I mean, again, the robotics and spintronics, and Internet of Things. There are a lot of exciting things are happening. So really, organic semiconductor and organic electronics has a lot of bright future. And I mean, a really humble request to all researcher working or those who wants to pursue this as a research career, particularly for students, there are a lot of exciting opportunity for you guys to contribute. So looking at the particularly dyes and pigment, if you see, these are all nice colorful compounds. I have put some chemical structures, starting with some sort of a anthranthrone type of, or might be indigo. Our gene pant, most of the blue gene pants, the blue color comes from the compound called as indigo, which is given here, the blue color. Then the Ferrari car, which is a very expensive sports car, the red color comes for that. Ferrari colors coming from the Ferrari dye. I have done a lot of significant work, I'll explain you shortly, which is a red color. Then there is another dye called as a Vat Orange 9, which can be also utilize it for various functional material for functional devices. Then some of the kind of a perilene and naphthalene bcimide type of dye, violet-gene, and I mean anthraquinone, and copper phthalocyanine, which is a very well-known dyes and pigments. So why those materials are interesting? Since I'm a synthetic chemist, but we do also look at the electronic devices. My passion is to make this colorful material in the lab where we can do a lot of interesting chemistry. And looking at this picture, that gives some sort of a stimulation, as well as my virtual background, that clearly tells that I love colors and color is my passion. So by changing this various emitting color, or might be absorbing color, or optical property tuning, we can really make a lot of new compound, and that's what we call as a molecular engineering. So we can do this molecular engineering by taking the chemical functionalities in the backbone, and we can have a very exciting new high performance material out of it. So particularly the donor acceptor type of materials, which has this electron donating molecule and electron accepting molecule, which are sitting in a backbone. Once we put them together, they form a donor acceptor type of material. Those are a very famous material these days. And if you look upon transistor curve on my right hand side, you can see that some donor acceptor polymers, they are giving the charge carrier mobility, which is very important kind of aspect for the transistor. They are almost close to the polycrystalline silicon, getting value close to the 10, or even I think some of the Stanford people reported close to 40. So why it is happening? Because the donor acceptor interaction, we can reduce the pi-pi stacking distance. And as the pi-pi stacking distance get reduced, since the semi-crystalline nature of this polymer backbone enhances, the charge carrier mobility gets very high. Because of this crystalline domain, the charge can easily hop upon the electrical bias. And I mean, by putting this donor acceptor combination, we can really make the strong donor strong acceptor, or weak donor weak acceptor, or strong donor weak acceptor, this permutation combination, and we can really make a lot of interesting material out of it. So particularly today's talk, I will be giving first about the transistor, then later on about the solar cell, and slightly I will speak about the display in between. So looking at the particularly transistor, I mentioned to you, this is a 3-terminal device. It is the same like switch. I mean, as you know that if we use the tap at home, we open the tap and then the water comes. So water is nothing but the flow of current. If we close the tap, water completely stops. There is no water leakage, means your switch is perfect. But if still there is water still dripping out upon closing the tap, it means that your switch is faulty. So this is the same thing in case of a field effect transistor. Upon applying the gate voltage, the source and drain creates the channel, and that generates the current, and that current can be of a p type, that can be of n type. and that can be of both P or N. That's called as ambipolar. So P-type or P-channel transistors having the holes as a majority charge carrier, N-type has electron as a majority charge carrier, and ambipolar has both charges can flow across source and drain. So and particularly looking at some of this new exciting material like 2D material or graphene is a wonder material, and why the graphene is not that successful in electronic devices, particularly in transistor, because the graphene material has a very small band gap, and due to that the on-off ratio, when you apply the gate electrode voltage, then transistor is on, but you stop the gate voltage applying, then the transistor is off. During the off state you should not get a leakage current, but in case of a graphene you get a huge amount of leakage current, and that's what the on-off ratio values are very lousy, close to 10 or something. Whereas in case of organic field effect transistor, using some of our organic material, we can reach this switching value close to 10 raised to 5, 10 raised to 6, and then we can consider this is really a very good switch. So this transistor can be utilized for various purposes. First of all, we can expose this channel semiconductor to the gas as a sensor, or might be a liquid. We can put up a pressure on this semiconductor, and then we can take a dielectric, might be a rubbery or might be a soft material there. We can act as a pressure sensor. So like artificial skin for future robotics and all, this type of artificial skin plays important role. Then you can create a light across the channel. That is also possible. It is called as a light emitting transistor. It means that from source and drain, you inject the holes and electrons, they recombine, they form a photon, and then they generate, it is a combination of the transistor plus light emitting, I won't say the diode, it is a triode rather, but it emits the light. In the transistor, the light emission happens. It means that in a future display devices, you don't require a special background transistor circuit to run your OLED, but rather your transistor itself can emit a light, and which is a very new kind of a state-of-the-art device people are looking at. Even for like CMOS type of, or might be this photo detector, the cameras which utilize for low light condition, taking pictures and all, you require the photo detector. So the transistors can be a very good photo detector. They can detect in presence and absence of light, how the current varies and all that. And they can be also useful for memory devices, where you put up deliberately some nanoparticle, they act as a trapping site where the charges get trapped, and then we can read in and read out the memories where the charges get stored via hysteresis. So looking at the organic thin film transistors, they have a lot of interesting application. I mentioned to you for stretchable logic circuits. And if we combine like P-type and N-type transistor together, you make a logic circuit, CMOS, flip-flop, inverter type of geometry. And this is how the microprocessor has all those devices coming together as in a chip. But again, making organic transistor-based processors for future is possible, but I mean, there are some challenges about the stability and all, but people have tried to put at least quite a huge number of like 10,000 transistor on an A4 size paper. But again, competing with the current Microsoft, Pentium chip or whatever, we are not nearby there. I'm not saying that we are competing with again classical those transistor chips, but organic is reaching up there for certain application, not really that high performance computing or where the high power or high speed require. But I mean, this totally depends on type of material, and it is possible might be one with graphene because of a very high mobility. So high mobility is very important for transistors. Second is a low threshold voltage. On-off ratio should be high, and then it should be stable in air. So looking at, I was mentioning to you one of the die called as a DPP. I usually show this work quite often because my contribution in this field is very significant. So DPP is a serendipity happened in a BSF lab, rather Ciba-Geigy. It has been now overtaken by the BSF, but there is a guy called as a Iqbal. He wanted to synthesize some azitinone, but accidentally synthesize this shown compound, which is a diketopyrrolopyrrol. That's what we call as a DPP, which is having a 2 ketonic group. And pyrrolopyrrol, you know the pyrrole structure, 5-membered string, they are fused together. That's what is a pyrrolopyrrol having the 2 ketonic group. So this is a very famous dye, Ferrari car they utilize for automobile coating application, and still this red color coming for the Ferrari coming from this dye. And looking at this particular dye, I mean, we made some new derivatives of this dye to utilize this dye in electronic devices because of the conjugation, because of some interesting electronic properties, it is planarity and all. And this is some sort of, again, synthesis slide where we can take any aryl carbonitrile 5-membered or 6-membered ring and converting that to the one like this aryl substituted DPP, and then we do the alkylation on this nitrogen side where we can put the solubilizing group and we can make a solution processable DPPs or diketopyrrolopyrrole, and upon bromination we can make a dibrominated analogs, and then later on we can do some chemistry or polymerization to make. And you can notice here like the phenyl and thiophene and furan and thienothiopene, we can make a different colored kind of a DPP dyes, and they can be useful as a ambipolar P-type or N-type material depending on what type of the materials, or I mean building blocks we are putting up. So I'll show you a few examples. This is the polymer which we published in Advanced Material in 2010. That time I was working in Singapore. So we took up this thiopene carbonitrile and then converted to this thiopene substituted DPP. Later on, we alkylated this thiopene DPP, which we made a soluble monomer, and then later on after bromination, this dibromine derivative we combined together with the boronic acid, boronic ester of this benzothiazole, which is commercially available. The dibromo we converted to the boronic ester here, and upon putting these two together, which we can make polymer. So this coupling is called as a Suzuki coupling. The guy from Japan, Akira Suzuki, who got a Nobel Prize for this coupling, where the two halogens can react with the two esters group and we can make the polymer. So this is like some sort of a donor as a thiopene, then this is acceptor donor, and this is acceptor. So we make a donor acceptor type of polymer. And upon this polymer in a bottle shown here, which is a very low band gap, I'm not showing the all optical data here because of the time, I have a lot of slides. So I just kind of showing you some important glimpses, but band gap of this polymer is close to 1.2 electron volt. And as I mentioned to you, if you can tune this band gap, you can induce either P-type, N-type, or ambipolar. In this case, band gap is low. That's what we get the both holes and electrons as a kind of a charge carriers in the channel. And this is like the typical example of ambipolar transistor, showing the typical V shape, having electron and hole mobility. And here is a hole mobility calculated in transistor geometry, top contact, bottom gate, having a silicon dioxide as a commercial available. And then we put up this polymer thin film on a silicon dioxide by giving some self-assembled monolayer treatment, and then putting source and drain as a gold electrode, and then completion the transistor, and then applying the sweeping potential across the gate, we can get a source and drain current. And this is what the output and transfer characteristics. So once we apply the gate voltage, it is a transfer characteristics. And once we take the IDS VDS curve, that is the kind of output characteristics. And then from that we calculate the charge carrier mobility, and which is a very symmetrical. If you wanted to make a future CMOS type of circuit where you require the kind of discrete P-type and N-type bringing together and make a PN junction. But in this case, the beauty of this material that you have only single transistor which operates in a both regime hole and electron accumulation mode. So you don't require a discrete P and N. The single device can act as a kind of, the logic circuit component. And here, looking at this polymer, this is in collaboration with Italian guys. We did some nano imprinting style, putting up this polymer as a solution, and then between source and drain as an electrode, gold electrode. And by putting PDMS stamp through the protrusion and having this spacing between the between these two protrusion side of the stamp, we got this wonderful nano strips across the source and drain. And here you can see a same image where all the polymer nano strips are in between. This is a gold electrode, and between we do have a polymer nicely organized. And these are some of the, upon annealing, how the X-ray data is changing, then crystallinity changing. And what we did, we connected the two transistors together, and then we got this inverter using the organic based transistor. So electron mobility and hole mobility of this particular polymer, upon doing the nano strip, we can enhance the mobility value, electron 1.45 and hole mobility 0.70. See, the same polymer which we publish in advanced material, we got mobility 0.40 and 0.35 just by doing the simple processing engineering. Here we enhances like a 3 times higher the electron mobility and 2 times higher the hole mobility. It means that not only making the material, but also you develop some kind of the nano engineering or nano surfaces by doing this type of lithographically controlled, wet lithography controlled techniques, where we can really push molecule to organize in those nano region in a fashionable way that they can enhance the mobility where the crystallinity gets high. So upon putting this two transistor V in and V out, that is the inverter, and then the gain value which we recorded close to 70. I think the highest one was a 105. Actually, we tried this work to publish in a Nature, but since it was published already in advanced material, the polymer structure, we couldn't get it, but we are happy to get it published in a nano later. We got also core picture for that. And this is the another polymer. So we just change it from kind of thiophene to the furan, and then we move furan DPP, and this is again, you can see color of the polymer, then AFM data, and in this case now mobility value, we push up 0.61 centimeter square per meter for hole and electron 0.67. So we continuously trying to improve these values here. And we put up exactly the same backbone what I showed you in earlier slide. Only the difference between earlier polymer and this polymer, instead of sulfur, we do have oxygen here. And oxygen, this is called as a furan. Furan is a biodegradable molecule, and which is, having a very good environmental friendly molecule, and we wanted to make some sort of a new material and also enhance these values, and here we shown that one. Then we come up with another building blocks called as a difluorothiophene. We did again the steel coupling. When you take these two halogens and combine them with a 2-trimethyl-tene or trialkyl-tene compound, this particularly coupling called as a Stille coupling. The guy called as a John Stille from United States, he discovered this coupling reaction. For polymerization, you require these 2 reactive sites to make a long chain compound, and we can really make a high molecular weight polymer. And compared to the small molecule, polymer has a beauty that we can make a nice film and all. You might have noticed in those bottle I showed the pictures, polymer was forming like a film and nice flakes, and we can really make a nice quality film out of it. So again, in this case, the reason of showing this slide is that, as I mentioned to you, most of our earlier data where we utilize chlorobenzene or chloroform as a chlorinated solvent, and industrial community usually, if you wanted to make this as a commercial entity or, kind of do the licensing, actually some of my DPP we licensed to the US based company called as a Corning from Singapore work, and they were asking like, can you change instead of chloroform might be a environment friendly solvent, and then we come up with a non-chlorinated solvent called as a hexane, and we made this new material, and then using even hexane, in this case we can achieve a very good hole and electron mobility again with ambipolar type of polymer. So again, it is a this furan is a donor, acceptor donor, and this whole moiety acts as acceptor because of this fluorine, which is electron withdrawing halogen. You know that fluorine has a very high electron negativity, and that becomes the electron acceptor molecule, and so we can make this band gap engineering as well as the charge modulation, either p-type, n-type, or ambipolar. Now looking at this polymer, this is like, here we put up electron donating group called as a naphthalene. Acenes are very well known, as most of the organic electronic people, they know that pentacene is very classical semiconductor people are using. This is the small brother of pentacene, which we called as a naphthalene. There is another brother, might be this called as a sibling, called as anthracene, and which can have these longer acenes having the this 6-membered benzene ring can fuse together. So this is more donor. So donor, thiophene donor, again, this donor only, this is only one acceptor. We have 4 donor. So we have a more donor as a majority. That's why you can see we get a whole mobility here, and whole mobility values are quite high, 1 centimeter square per voltage second. This is again the typical curve. We apply the negative gate voltage bias. We get the positive kind of the whole mobility, and then here is the gate voltage values and how this saturation mobility shows this out. This is like transfer characteristics in this output characteristic in the AFM data. So most of this polymer which we develop here by DPP or Ferrari red pigment one, they have an ability to form a nice fibrillar morphology upon annealing. And you might have noticed from room temperature to the 140, they form a nice fibrillar or fibrous structures as a nano rod type of, and they sit pretty well in between source and drain, and the sort mobility values are quite high. Then we put up another fused structure, which is a thiopine and bithiopine. And here you can see, as you take the closed structure versus this is an open structure. So closed structure, our pi stacking distance, which we calculated from this X-ray diffraction data from taking this pi stacking, I mean this second diffraction peak and having this Bragg's equation n lambda equal to 2d sine theta, we got this value of d-spacing or pi stacking of those polymer backbone. This polymer usually form a two type of stacking. One is called as a face-on and another is called as an edge-on. So this is a typical example of a edge-on. Face-on is a very feasible for the solar cell type of, where the transport happen vertically diode. In case of a transistor, your transport happens as a horizontal because your source and drain are sitting, and your polymer thin film and dielectric you know, the interface where the conduction happens, so which is a more horizontal. So in this case, the this edge-on is very crucial, and these both polymer form an edge-on. And the important part, how we can enhance the mobilities of this polymer, the main beauty is that by doing this nice molecular engineering aspect, we really want to push this value close to might be higher than polycrystalline silicon. Is it possible to make 100 mobility or 400 or 500 or higher the values is better? So we're trying to push this mobility values, and that's for enhancing the mobility value, this pi stacking distance is extremely important. So this is around 0.371 nanometer, 3.7 angstrom. This is 3.75. So you can see that just by changing the open versus close, we can tune this pi stacking distance, and that's what I showed this slide. And then like just by minimum annealing, again the industry people were telling us that can you reduce this annealing temperature instead of going crazy 250? We don't have a plastic film that can tolerate of that high temperature. We just wanted to have some material they can be annealed very mild condition, and then still we get a high mobility. And this particularly two polymer just anneal at 100 degrees Celsius, we can achieve a very good whole mobility of 1 centimeter square per voltage. The second. So then we put again another longer conjugated structures called as a dithiopine here, and then look at that. This is a donor, and only acceptor. This is a p-type again polymer, and then p-channel transistor. We can push mobility value 4.2. So as the important design rule is that if you put up a very fused aromatic backbone in a conjugated backbone, then you can really push this mobility value. But again, you have to compensate these alkyl chains, because if you put too long fused backbone, then your polymer becomes like a rock and you can't make a solution out of it. So we need to take a long alkyl chain to make them a solution processable inks, and then we can print them or we can spin coat them. So the polymer, I mean on-off ratio values and then mobility values are shown here. Then we did some kind of, again, in collaboration with Texas University, Professor Anando Dabalapur, USA. This is, again, taking another polymer. They did some sort of a device engineering in a way of silicon dioxide. They put up the kind of, again, the gold as a electrode here. So it is like a bottom contact type of devices. And here, titanium is the best kind of material which reduces the work function, and then that's what they have utilized it. So taking this dielectric material is also important for the transistor. If you take the low K and high K or dielectric material and their combination like zirconium oxide and then one of the polymer, then we can make this just device engineering, and we can reduce. Really the threshold voltage is very important, because most of the time people report the organic transistors and then the values of your threshold voltage are very high, like -20, -30. If you want to make a low operating voltage transistor for displays or for various application, it is good to have this threshold voltage value less than 2 volt or 1 volt. And in this case, we got this low threshold voltage because of this nice device engineering and combination of high K, low K dielectric. And again, on-off ratio values, it is 10⁻⁷. Again, if you want to use this as in a microprocessor or might be type of circuits where industry wants to put them in a flexible type of prototype, they wanted to have this bottom contact. And for that, they want the channel length, because channel length is very crucial. Channel length is the length between the source and drain, 2 electrodes. So if you have a shorter channel length, the more devices you can put it in a kind of circuitry, and then we can have a higher speed. So this is like a 4 micron. Most of my earlier slides where I showed might be a 50 micron channel length devices, but this was the lowest one. And there are some limitations, I mean, to make the very small channel length devices because of the lithography and I mean some of the nano fabrication limitations. Okay, so using some of this polymer, which we can now push the mobility in one case like 10.5, we got the high molecular weight. And I mean, this is a scientific report paper where we demonstrated on a flexible plastic and then all the stability study and all that. If you are keen, just look at that paper. But the main message is that we really can push this mobility value is very high, and this has been patented successfully. We got some commercial benefit out of it, very glad. And then we make the whole range of this polymer, and then sort of got almost close to, might be, I made 50-60 polymers and published a lot of 50-60 papers alone on this polymer by in collaboration with my colleague Yuning Lee, who is a professor now in Canada. And I mean, we believe that using these polymer rings, we can print them and make a flexible circuits. So again, looking at some of this polymer, which we can also utilize them for a sensing application. I was mentioning to you, you take a transistor, expose them to the analyte, and then we can see response of analyte versus the current and threshold values, or might be sub-threshold swings and all that. So this is simple polymer, just synthesized by me. And then it is in collaboration with Hossam Haik in Israel Institute of Technology, Technion Israel Institute in Israel. And then he's a very well-known, and he does a lot of work on cancer sensors or breathing sensor. Usually person who develops the cancer in his body, he develops some sort of a volatile organic compounds. So once those volatile organic compounds comes from the breathing, and if you have a small sensor chip, you just put up close to the mouth, those volatile compound can be identified, and then you can notice that whether the person has developed some cancer symptoms, and then early detection can helpful to give a treatment. So he does a lot of that breathing sensors, and he got a lot of funding from Bill Gates Foundation. So he's a really very well-known person in sensor field. So he took up this polymer, he made it the sensor called as xylene. We got the cover picture for that. Xylene is a very notorious chemical. Once we expose this, I think more than 100 ppm xylene exposure every day, or might be a longer period of time, which is which has a very nasty effect on cardiovascular or nervous system and a lot of other type of diseases. And that's what National Institute of Health, United States, they mentioned that if there is a technology which can detect less than 100 ppm of xylene, that will be fantastic. And in this case, we come up with this transistor-based sensor where we can detect xylene up to 40 ppm, which is very significant result, and that's what it got highlighted on advanced material. And we can see like 40, 60, 160, 200. 240 and 320 various concentration, how the response is. The beauty of this polymer semiconductor or transistor is that since it is ambipolar, we get two types of the device parameter always, because whole accumulation regime as well as electron accumulation regime. And that's what we see these 6 curves. So 6 curves are nothing but, you notice that threshold voltage is nothing but once you expose the analyte, then how the transistor starts on, because of the analyte and polymer semiconductor interaction, the threshold voltage varies, and that is a concentration dependent. So that is a delta VTH. Delta ME and mu E, that is the electron mobility with and without exposure. Then del S, which is a sub-threshold swing. Del VTH, which is a whole type of mobility, and and then the difference between the whole mobility before and after exposure, analyte. So whole electron and sub-threshold swing, these are the 3 important parameters which we can do in electron mode as well as in whole enhancement mode. That's what we get, the 6 parameter. And using some principal component analysis, this PC1, we can get this 3 isomers of xylene, which is orthoxylene, paraxylene, and metaxylene. Xylene has a benzene structure with 2 methyl groups. So if methyl group is close to the terminal methyl group, it is called as a ortho, then it is on a 2nd position meta, and then the 3rd position para. So this is very critical to find out structurally very similar analyte to get analyzed by a sensor like this. And we first time demonstrated having a very structurally similar isomer, still we can identify the difference. And that is really one of the very very nice outcome came from this collaboration. And then what exactly happens in terms of when xylene comes in a contact with polymer semiconductor, the simple reason, like we did some theoretical modeling. So this polymer has a HOMO-LUMO values, which is like a conduction and valence band, in other words, which we call highly occupied molecular orbital or lowest unoccupied molecular orbital. And once xylene analyte gets absorbed by this polymer semiconductor, slightly the HOMO-LUMO shift happens. And as HOMO-LUMO goes up, you can notice it upon xylene comes in a picture, HOMO goes up and LUMO goes up. So what happens, holes gets injected much more effectively once xylene gets absorbed, because HOMO value is very close to the Fermi level of the gold, whereas without analyte it is a little bit far, so the whole mobility is a bit slow, or might be the threshold voltage is high. In this case, threshold voltage is low, mobility is high, and this is what it's happening with respect to the xylene, and that is like some sort of we did this study. So we just published a very high impact journal called as a Chemical Society review about all these transistors. How these organic field effect transistors are really a game changer for future medical electronics or Internet of Things, and I mean wearable electronics, and I mean there are a lot of interesting aspects. If anyone is keen, this is really a very highly respected journal having impact factor close to 42. Just got published. My another student Neil Liu from China, he made another big contribution. I think I have to little bit move fast. Sudham, how much time I do have? Hello?
5 minutes, 5 minutes.
Oh, really? Okay. So we do have another new dye, the naphthalene DPP dye, where we kind of utilize this dye, and we made a different type of their derivatives. Here are the colors of this dye. And again, utilizing in transistor, we can get a mobility of 0.01 to 6. I think I will go with quickly a little bit. The important things here, this dye, which we can grow as a single crystal, and single crystal transistor is another interesting aspect. And you can see nice colors and crystals, needle-like. We put up those needles. I mean, we first make the thin film and measure the transistor mobility, and we got this value 0.05 and 0.01. The mobility values of these materials are rather low compared to the earlier values, which I shown very high. But the another things, don't forget that this is just the small monomer, just the small molecule. It is not the polymer. And still for monomer, this value is very high. And then we make the transistor in a single crystal. It means that the single crystal we put between the source and drain, and then we got the mobility values of those quite high. And then the reason is simply stacking and all. This is in, again, we did some light emitting diode in collaboration with, I think, Sudham. Sudham has done some nice work on this when he was in Taiwan, and we made some OLED devices, and they operate only on a 4 electron volt, hexyl substituted and octyl substituted. And here is the OLED, a small display you can see here. And I mean, this is the geometry like ITO coated glass, and I mean P.dot PSS, and our material as a emitting layer, and then host TCTA guest. Our material as a host, and then we made this TPBI, and then we completed this device. So then we got this, I think the solar cell. I have to, so it might be time is too short, but I'll just quickly show you some of this organic solar cell technology, where a single crystal silicon and second generation and third generation, which is emerging, perovskite and organic and dye-sensitized. My group is working on perovskite, and then we are particularly developing some new materials. The perovskite is a very nice high quality material, and looking at the solar cell data, now the perovskite is heading up close to 26% efficiency. This is one of the fast moving, highly efficient solar cell devices in the world in terms of I mean the performance wise, but the stability is a big issue. And this is some sort of, again, the schematic, how holes and electrons get separated. And we wanted to the ETL and HTL. ETL is electron transporting layer, and HTL as hole transporting material. And then we get the electricity out of it. So the David has done some nice work on this line. I think I will skip a few of the slides because of the time. I think what I will show you might be one of the quick video, I think, which can give you some sort of idea. Just to listen that video, and then you'll get and then I'll. Actually, yeah. Sorry for the little taking your time. This has been kind of Wiley has made a nice kind of story about this, and it has been also channelized on Australian news channel. Yes. I think I'll just kind of might be it's because of time. I'll just skip on that. But we make a lot of high performance material, and I mean you can see we got a lot of cover pictures. We made also OLED, blue, green, and blue emitting OLED devices. And again, I mean, yeah, there are a lot of dyes and pigments we utilize. There are a lot of, I mean, we publish a lot of high impact papers in energy and environmental science, advanced energy material. And recently, one of my, this is really, I mean, just I'll take 2 minutes and I'll stop my story. Recently, we made OLED devices using human hair. And this is one of my PhD student, Amandeep. So what we did, we took up the, literally this is the barber, which is very close to my apartment when I used to live. So we took up the hair sample from him and we make a carbon dots solution. And then we put it on an electrode and we make a flexible OLED, and which got really a very a lot of coverage, including Yahoo and all. So because of time, here is like the details of those flexible devices, what we did. Since human hair contains the keratin as a protein, amino acids proteins are polymers of amino acids. So once you heat human hair, it forms the carbon nanostructure, and the amine group present in a human hair or keratin that dopes the carbon, and it forms a nitrogen dope carbon dots, and they can we can do some chemistry on the kind of their surfaces, and we can make their highly emitting carbon dot, and we made a display out of it, so which was just published. I think with this, I'd like to thank all of my collaborators. Particularly, I'm thankful to Australian government for giving me this future fellowship. And then thanks to the Agency for Science, Technology and Research. This is my group, kind of a couple of years back, all the members, Japanese professor, he visited our lab and we had some social gathering, including my family members, and like to request people who wants to publish papers. I'm in editorial board of Flexible and Printed Electronics. And with this, I'd like to conclude my talk, and sorry for taking extra minutes.
Thank you, sir. Thank you very much. You had a very fabulous presentation. So we have some selected questions.
Yeah.
The first question from chat box of YouTube channel. What about the stability of organic material based devices? And it is asked by Prashant Bhaviskar. So please.
Yeah, it is a very good question, and usually I get these questions in many conferences. Actually, I mean, the stability of materials really depends on this energy level kind of aspect. Particularly, most of the polymer, the one which I showed in a scientific report, where the 10.5 mobility we get, those are very stable devices. Even we put up those transistor devices for 2 to 3 months, and we measure the mobility values are still kind of reproducible one. For solar cell also, it is possible to get a very good stability. But again, the important thing is, if your energy level of the materials, the HOMO value which we called, if it is like 5 or 4.9 or 5.1 electron volt, they are vulnerable to oxidize very easily. So you should make a new material which has a HOMO value like 5.3, 5.4, or lower the HOMO is the better the kind of you get the performance. This is for P-type material or P-channel or whole mobility material, either for transistor or for solar cell. For N-type material, getting the stability is a very critical. And until and unless you push LUMO values close to 4.3 or 4.4, and there are very few material in the literature, they can you can make the material having a LUMO value 4.3 or 4.4. They may be 3.9 and 4 or might be 4.1. Some of our ambipolar material which are having a LUMO value 3.9, we get a very high hole mobility outside of the glow box, but electron mobility slightly get affected. Since this electron mobility kind of conduction in a presence of moisture or oxygen, it is indeed a critical. But I mean, again, if you wanted to make the future devices of those type of material, there are some technologies where we can have a encapsulation done, having some barrier film you put, and then device is kind of a sandwich between the barrier film, the oxygen will not penetrate in, and then we can utilize it for future applications. Yeah.
Okay, thank you, sir. The second question is asked by Yogesh Patil. And the question is, what is the future of graphene-based materials in solar cell application?
Graphene is a really nice material. I mean, it is a nice 2D material, strongest, toughest, having a very high mobility and all. The biggest problem in a graphene technology in the whole world is about how to make a graphene on a large scale. Because currently technology having a chemical vapor depositions where we have to use some gases to kind of convert those gases to the graphene type of single layer atomic flat structures. But using, again, I mean, as you know that the graphene story, graphene was invented by using the scotch tape, by taking the graphite as a pencil material, and you put a scotch tape and remove the first layer and look at under the TM, you get this kind of a mixture of monolayer plus bilayer, trilayer or whatever. So getting the single layer graphene nicely clean is still big challenge, and only few techniques like CVD can give a very nice and I think the vapor size of might be 4 inches and all has been kind of published by Koreans, but I haven't heard a big size graphene film is really a big challenge. And in order to bring this graphene technology to the future electronics, until and unless someone come up with a like, you know, the high throughput or might be a high large scale manufacturing of making high quality graphene, then there will be a huge kind of that is the bottleneck. And if someone does that, that will be really a game changer. And we believe that scientists are trying to explore these various possibilities. And again, I mean, in a community, sometimes people a little bit mislead this field. Graphene, honestly speaking, I used to ask this question many times. Graphite, graphene, I mean, these all carbon nanostructure. Once you have I mean, more than 20, 30 layers, I don't think which we should call it as a graphene, because once many structure comes in a picture, then they really lose the property what graphene should have: atomic flat, one layer or maybe two layer or max three layer. If it is more than multiple layers, then it is not really a graphene. And currently people are using like reduced graphene oxide, RGO, or might be other type of graphene. Under the name of graphene, they sell these materials which have some interesting properties. But again, I mean, they are not as like graphene. I mean, they're not, I mean, they might have a lot of defects in that, and that's what they have this kind of, the processable inks which commercially available based on, I mean, and they sell under the name of graphene. Yeah.
Okay, sir. One more question, please.
Yeah.
Have you evaluated these chemicals toxicity related to human? And the question is asked by Vinod Ayrao. So please, sir.
Yeah, it is a very good question. I mean, that is what we are moving little bit now. My future study would be to make the green electronics. Just we recently published a review article in Advanced Material where we are talking all about the green electronics. Means that how we can take the human health feasible materials and those type of devices for future body embedded devices and all. Particularly looking at some of our structures here, I mean, sulfur-based, thiophene-based compounds are not really, they have done some evidences, the bioassay. Ourselves, we haven't done any biological study of our materials, but there is a one chemical compound called as a P.PSS, polyethylene dioxythiophene polystyrene sulfonated dope, P.PSS, which is a commercial available material, conducting polymer, which has been utilized as electrochemical transistor material for bioelectronics application, putting on a brain and measuring the brain signals, those people having a schizophrenia and all brain disorders, and monitoring those things. So for those type of devices, I think they did the bioassay, and the kind of obtained results are very promising, and they does not have any adverse effect. But again, the guideline is that whenever you make a material, better you make a material which is nature inspired and which can be more biocompatible. Yeah.
Okay, thank you, sir. Thank you, Professor Prashant Sonar, sir, for a very interesting talk on functional materials for optoelectronic devices. The colorful materials for varied optoelectronics devices such as solar cells, organic light emitting diode, organic field effect transistor, biosensors, and flexible display technology. Your deep understanding of molecular engineering of organic materials enlightened us, and we really look forward to hear it from you, from your lab, some breakthrough research for advanced optoelectronics devices, particularly the field effect transistor, organic solar cell, and biosensors. Thank you very much. On behalf of organizations, I would like to thank you, sir. Thank you very much.
Thank you for giving me this opportunity to my college and all the gurus. I'm giving my bow respect from here. I mean, I would like to visit you, all of you, sometime when I came next time. I hope COVID situation gets clear soon, and wish you all the best, everyone. Stay healthy and kind of, praying for all of you to stay safe. Take care.
Thank you, sir. So please, you are requested to just stop the share screen.
Yeah, I'll just stop the sharing. Yeah.
Yes, thank you, sir. Now, dear participants, let us move to the last section of this international webinar, and that is the valedictory session. We have for this valedictory section two chief guests, Principal Dr. P.H. Pawar, sir, and Principal Dr. A.P. Khairnar, sir. And guest of honor for this valedictory function is Principal Dr. R.S. Patil, sir, from Shada College. So let us move to the valedictory session. And I would like to introduce the chief guest, Principal Dr. P.H. Pawar, sir. He is the principal of Z.B. Patil College, Dhule. He has been proved as the apex academic leader in the arena of Savitri Bainabhai Chaudhary North Maharashtra University. He is the former management council member of KBC NMU Jalgaon. And one more thing that we all know, that cycling is his best hobby, and sir has been cycled nearly 42,000 kilometers. So that is what we always inspire. Means he inspires us to be healthy by just applying such kind of exercises, and that is what we already he has set the example for all of us. He has been guiding, means he is research supervisor in his subject. Uh, he is always been there for various university committees. He is not only an able administrator, but he is also noble-hearted man. He always used to guide all of us, and that's why the gentility of sir always inspire us. So I would like to request Honorable Principal Dr. P.H. Pawar, sir, to have webinar remarks, sir. Sir, please, over to you.
Thank you, Chavan sir, for a very inspiring words from your lips. Because today is Sunday, and I was very happy to say about your organization of today's international webinar. It is really international webinar because right from morning 10:30, we are listening three gentlemen fellows which are not sitting in India. Particularly Rampal Sharma is there, Nishad Deshpande is there, Sonar sir is there, and Mani sir is our friend. Definitely, as also I'm working with the same era in Optoelectronic Devices, I'm little bit, I'm working as an administrator. I left so many things while doing the research, but as soon as I joined today's webinar, I'm extremely happy because I got the different areas of optoelectronic devices, particularly talking about the Professor Sonar. I'm very happy. The guy from Maharashtra and guy from Sakri College doing very well in Australia. That is a proud moment for us. Basically, because that is always I'm thinking about the organic materials, and definitely how to deposit the organic materials. It is a little bit challenging work, and what sort of work carried by this fellow and his team. I want to congratulate them. Basically, the people living in Sakri, uh, they are conducting such type of academic webinar, and I extremely happy because all the four speakers, including Dr. Fasesar from Indore, all are very gentlemen fellow in their respective areas. Basically, that is a I want to listen these fellow. I'm very serious. Right from morning to till end, I'm here because this is one of the good day in my life in COVID session because I listen some academic things today, and definitely the person behind is that even though Iris is my colleague, classmate, and friend, but our mentor is main. That is Dr. Sanjay Sonone sir. He is a leader of organization. He took initiative in all aspects of the problems of the teacher fraternity, and definitely he is going to be retired on the 30th September because we will missing him. But I hope that we will not miss him because we will make some possible arrangement for coming 2 years, and he will be live with us. He will join with us, and definitely he will. I hope that he is a very uh, dynamic personality, always helping us to solve the problems or ask the questions, how we can go through these problems, how we can rectify the problems of the teaching paternity. So I'm very extremely happy because these people are really, uh, I want to congratulate all the team of Sakri College. No doubt, the people from physicists, people from chemistry, people from English are conducting the webinar very well. And I want to congratulate the all teams. And also I want to say thanks to the management, particularly our Honorable Dada Sahib Suresh Patil, because he is also my mentor, and he also gives a free hand to our friend Eraser to conduct such academic activities. And I hope that I want to wish once again our friend Dr. Sanjay Sonone sir to have a long and healthy life in future, and hope so he will with us once again. I want to thanks to all participants here, and I want to congratulate the all teams of the Sakri College. Thank you.
Thank you, sir. Thank you very much for your kind words. Your blessings are always with us, and that always motivates us to conduct such academic activities. Thank you very much. Now, I would like to introduce our chief guest for this valedictory session, Honorable Principal Dr. A.P. Kherna, sir. Sir has been principal from more than 12 years. He is the former officiating dean of languages, North Maharashtra University, Jalgaon. He has also worked as chairman, Board of Studies in English of North Maharashtra University, Jalgaon. Presently, he is the Senate member of North Maharashtra University, Jalgaon. He has been also worked as a member of various committees. He has also organized various kinds of academic activities. He has guided 6 students under his able guidance. 6 students have successfully completed their PhD degrees, and I am very proud, and that I am one of his student. He has been guide, mentor, and also a very gentle human for all of us. I request Honorable Principal Dr. A.P. Khernar sir to have few words on this particular organization of the webinar. Please, sir.
Am I audible, sir?
Yes, sir. You are audible, sir. Please.
Honorable patrons of this international webinar organized by Vidya Vikas Mandals, Sitaram Govind Patil, Arts, Science and Commerce College, Sakri, Honorable Abba Sahib Suresh Patil, Secretary Vidya Vikas Mandal, respected Tai Sahib Mangala Tai Patil, President Vidya Vikas Mandal, Honorable Sri Chandrajit Patil, Vice President Vidya Vikas Mandal, Honorable Professor P.P. Patil, Vice Chancellor Kavitri Bahinabai Chaudhary, North Maharashtra University, Professor P.P. Mahulikar, Pro Vice Chancellor, Honorable Kavitri Bahinabai Chaudhary, North Maharashtra University, Professor B.V. Pawar, Officiating Registrar, Kavitri Bahinabai Chaudhary, North Maharashtra University, and Chief Organizer of this international webinar, Professor Principal Dr. R.R. Aire sir, Convener of this webinar, Professor Sanjay Sonone, Co-Convener Dr. Sudhab Chavan, Co-Secretary Dr. S.J. Nandre, and dear resource persons as well as participants and teaching and non-teaching staff of this college. Vidya Vikas Mandal's H.G. Patil College has organized this international webinar very successfully. Since morning, this webinar is going on. I mean, this webinar is centered around role of advanced materials for optoelectronic devices, RAM, AUDI. In this webinar, really international scholars and personalities, those who have been working in physics and electronics, have contributed. I know since my studenthood, I have been listening the name of Professor Dr. Devdatta Phase sir, I mean, who is authority in physics, as well as, I mean, resource persons contributed a lot. Professor Dr. R.S. Mane, Professor Rampal Sharma, Dr. Nisad Deshpande, Dr. Prashant Sonar. They have contributed a lot. I mean, what is going on in technology? What are the advances in technology around the world? And this international webinar is really thinking of such a type of technology, such a type of advanced technology. I mean, what is in the world? What is going on in the world in science and technology? Sir, I congratulate you with your team for organizing such a wonderful, very successful, and very excellent webinar, and that too international webinar. And this is a matter of pride and pleasure that this webinar is dedicated to great teacher of physics, Honorable Professor Sanjay Sonone, who is going to retire in the month of September 2020. Professor Sanjay Sonone is a renowned teacher of physics who is very much popular as a teacher, who has shaped and coined a number of personalities of students. It reflects through his alumni of physics. His role as a teacher is highly commendable. He is not only a teacher of physics, but the committed and devoted leader of NMUCTO. He is known for his justice. He always fights for the rights of the teachers. I mean, if I say informally a lot about Honorable Professor Sanjay Ji Sonone, he is our mentor, friend, philosopher, and guide. He has been office bearer of NMUCTO in different capacities at university, state, and national level. He has devoted his entire life in the interest of teachers and students. This is really a great contribution to academic field, or can say fraternity. At present, he is Senate member of Kavitri Bahinabai Chaudhary North Maharashtra University, Jalgaon, and working on different key committees of university. His contribution as a teacher and leader of NMUCTO organization can never be forgotten. He will be guiding star for the teaching fraternity in both capacities as an organization leader as well as teacher in the days to come. Dedicating international webinar as a sense of gratitude to his contribution is really a matter of pride and pleasure. And a salute to the work of Honorable Professor Dada Saheb Sanjay Ji Sonone. This is really great event you have organized, Honorable Principal Dr. R.R. Ahire sir, Dr. Chauhan, Dr. Nandre sir. I mean, as a gratitude to a great teacher as well as great leader, great teacher activist. I mean, it is really a matter of pride. Sir, I congratulate you for organizing this very wonderful webinar, and that too international webinar, as a gratitude, as a dedication to the great teacher as well as great organization leader. I mean, sir, you have organized this webinar, I mean, as a dedication to Honorable Dada Saheb Sanjay Ji Sonone, but at the same time, keeping in mind that what we can do during this lockdown time, during this pandemic time. I mean, we all people have been suffering from this pandemic. We are in lockdown, we are in confined situation. I mean, this is the historical period. I mean, we have not seen such a period, and we have been passing through this period. But as academicians, as teachers, if we remain silent, time will not spare us. So, Principal Dr. Ahire sir, Honorable Dada Saheb Sanjay Sonone, Dr. Sachin Nandre, and Dr. Sudham Chauhan, and teaching and non-teaching staff as well as patrons. Sir, you have done great work. I mean, you have taken the review through this international webinar, what is going around the world in technology, and that too in advanced materials, that too in nano material. I mean, the international webinar was really intellectual feast. I mean, it was perfect, both technically as well as content. I mean, it was really very fine and nice organization by H.G. Patil College. So I congratulate you, sir, on behalf of all participants, all scholars, and you have brought such a type of scholars as resource persons, those who are the masters, those who are the authorities in the respective area of electronics and physics, and you have bring them before the participants, and participants are really enlightened. I mean, this international webinar proved very informative, intellectual feast, and really offered insight and foresight for the budding researchers as well as teachers. So once again, sir, I congratulate honorable patrons, honorable principal of H.G. Patil College, my friend, Principal Dr. R.R. Aire, sir. We have organized this international webinar as a gratitude, or you can say as dedication to Honorable Dada Sahib Sanjay Sonone, who is retiring. I wish very happy, retired, peaceful life to Honorable Dada Sahib Sanjay Sonone. And I congratulate Professor H.J. Nandre, Professor Dr. Sudham Chauhan, Professor Dada Sahib Sanjay Sonone, and teaching and non-teaching staff, as well as Dada Sahib Honorable D.L. Torone. Sir, I congratulate all of you. And without your vision and mission, Honorable Principal Dr. R.R. Aire, sir, this webinar would not have been successful. So I congratulate you on behalf of my Adarsha College of Arts, my management, as well as on behalf of participants, to you, to your management, and to your entire team, sir. Once again, I congratulate you, and I thank you for giving me an opportunity to express my views. Sir, thank you and congratulations for organizing such an excellent, wonderful, and very historical international webinar by H.G. Patil College, Sakri. Sir, thank you. Thank you.
Thank you, sir. Thank you very much. On behalf of organizing committee, I would like to thank both of you, sir, Honorable Principal Dr. P.H. Pawar, sir, and Honorable Principal Dr. A.P. Gharnar, sir, for giving your precious time and for showing your good wishes. Thank you very much, sir. Now, I would like to invite Professor Sachin Nandre, sir, to introduce our guest of honor for the concluding concluding session, Principal Dr. R.S. Patil, sir. Dr. Sachin Nandre, sir, will introduce Principal Dr. R.S. Patil, sir. Over to you, sir, Nandre, sir.
Good afternoon, all of you. Well-known, dynamic, innovative, helpful, and generous personality, Principal Dr. R.S. Patil is working at PhD UP Mandals, SI Patil Arts, GB Patel Science, ST KV Singh Commerce College, Shada, District Nandurbar. His teaching experience in Junior College 1 year, UG College 33 year, PG College 23 year. He is the administrative experience. He is a principal PhD UP Mandals on the since 10th August 2060. Head of Department of Physics, PhD UP Mandals College Shada, Director and Coordinator of IQSC Shada College, Coordinator of NAC Steering Committee, Chairman of NAC Steering Committee 2017, Director of Yashwantrao Chauhan, Maharashtra Open University Nasik, Study Center of PhD UP Mandals Arts College Shada since January 2017. Study Center of PhD Art Science Commerce College Shada, District Nandurbar. He is also NSS Program Officer in PhD Mandal Shada College. Also Director of Academic Staff Society, Credit Society, Sir will be published 31 paper, FYBSc 30, 15 paper books, SYBSc 14, and research 2 books will be published. Under the guidance of Principal Dr. R.S. Patil, 6 students will be awarded PhD, and presently 5 students are working under his guidance. Sir also Secretary of Principal Forum of KBCNMU North Maharashtra University. Sir have various committees in KBCNMU North Maharashtra University Jalgaon. Member of Senate, already is presently member of Senate. Also 95 2010, and also he has present working on Senate member. Chairman of Board of Studies in Physics 2005 to 2010. Member of Examination Unfair Means Inquiry Committee 2005 to 2010. Member of Research Recognized Committee 2005 to 2010, and member of Grievance Residual Cell 2011 to 2015. This is the introduction of Guru Principal Dr. R.S. Patil. I introduce, and I will say to over to the Principal R.S. Patil sir to share his views. Thank you.
Thank you, Dr. Nandre. Good evening, one and all. Dignitaries online, keynote speaker, scientist and director of UGC DAE Consortium Indore, Dr. D.M. Phase. Leading researcher, Professor R.S. Mane, Professor R.P. Sharma, Dr. Nishad Deshpande, Dr. Prashant Sonar, professors, researchers, and students from all corners of the world in general and India in particular. Principal S.R. Jadhav from Rashtriya College, Chalisgaon, Principal Dr. D.R. Patil from R.C. Patel College, Sherpur, Principal Dr. P.H. Pawar from Jahin College, Dure, Principal A.P. Khairnar from Nijampur College, Chairman of this international webinar, Principal Dr. Rajendra Ahire, Convener and friend, philosopher and guide, as said by Principal Khairnar, Professor Sanjay Sonone, Co-Convener Dr. Sudham Chauhan, Coordinator Dr. Sachin Nandre, team of H.G. Patil College, Sakri, and friends, greeting of the day. Hope you are doing well in this pandemic caused by COVID-19. I, Professor Rajendra Patil, Principal of PHGP Mandals, Arts, Science and Commerce College, Shada, is here with presenting concluding remarks of this international webinar on role of advanced materials for optoelectronic devices. COVID-19 is a public health emergency of international concern, who declared COVID-19 as a global pandemic on 11th of March this year. Global researchers are working round the clock to find a possible treatment to save the lives and develop vaccine for the future prevention. India's proactive, preventive, and productive approach to fight COVID-19 pandemic started under the eminent leadership of Honorable Prime Minister of India, Sri Narendra Ji Modi, and Honorable Chief Minister of Maharashtra, Sri Uddhav Ji Thackeray. I, Principal Dr. Rajendra Ahire, Professor Sanjay Sonone, Dr. Sudham Chauhan, Dr. Sachin Nandre, and team H.G. Patil College, Sakri have converted challenge of COVID-19 pandemic into an opportunity to organize online international webinar on role of advanced materials for optoelectronic devices for researchers and students. Scientist and Director of UGC DAE Consortium, Indore, Dr. D.M. Phase, delivered a keynote address of this international webinar. He elaborated use of advanced and nanomaterials in thick and thin film form for optoelectronic applications. He explained how optoelectronic devices are responsible for conversion of light energy into electrical energy and vice versa. Professor R.P. Sharma, brainpool scientist presently working in Korea, and Professor of Dr. Babasaheb Ambedkar Marathwada University, Aurangabad, delivered invited talk on 2D nanostructure materials for electrochemical energy storage. He explained that nanocrystalline materials are novel polycrystalline materials with a grain size 20 to 80 nanometer. Nanoclusters of metals and semiconductors are considered as building blocks of future modern technologies. Leading researcher, Professor R.S. Mane, Professor of Physics, SRTM University Nanded, delivered second invited talk on recent advances in technology. In his talk, he had advised young researchers to concentrate on the problem and go for applications. He highlighted the properties of the material in nanocrystalline form are quite different and often superior to those of conventional coarse-grained polycrystalline materials, and also amorphous alloys of the same composition. At the outset, I take this opportunity to congratulate Professor Mane for establishing ever first COVID-19 testing lab under his guidance in his university, that is SRTM University, Nanded. This lab is the first of its kind established in any university of Maharashtra so far. In post-lunch session, smart Professor Dr. Nishant Deshpande, research professor from Korea, delivered invited talk on designing of smart materials for highly efficient optoelectronic devices. He highlighted on overview of optoelectronic devices, key parameters for optoelectronic devices, simple PEC for water splitting, and applications of some controlled nanostructures. In next session, Dr. Prashant Sonar, who is an alumni of H.G. Patel College, Sakri, now working as an associate professor in Queensland University of Technology, Australia, delivered a very nice invited talk on advanced functional materials for electronic displays and energy. He explained preparation of advanced materials and applications for electronic displays and energy devices. He focused on transistors, FETs, LEDs, diodes, and colorful solar cells during his talk. I would like to add, this international webinar is organized to honor our best friend, Professor Sanjay Sonone, who is going to retire from his position as a professor of physics of this college. Words are not sufficient to express my feelings about Sanju Dada. We admire his work, his service to the students, teachers, and stakeholders of higher education. I extend my best wishes to friend, philosopher, and our guide, Professor Sanjay Sonone. Professor Sonone assured me that he will be with us after retirement also. So let us hope that he will join us in a different venture. Say, I would like to congratulate Principal Dr. Rajendra Ahire and his team for painstaking efforts for organization of international webinar on role of advanced materials for optoelectronic devices in this tough time. Blessings and guidance from members of management of H.G. Patel College, Sakri is highly appreciable. The guidance of Professor D.L. Tonare, former principal of this H.G. Patel College, is highly appreciable. I take this opportunity to thank Principal Dr. Rajendra Ahire and his team for giving me an opportunity to share my views on this occasion. Thank you. Thank you very much. Jai Hind.
Thank you, sir. Thank you very much for your insightful concluding remarks. You have covered all the aspects of the international webinar. Thank you very much. And now I would like to request Professor Sanju Dada Sonone for vote of thanks. Dada, over to you.
At the outset, I, Professor Sanjay Sonone, very much thankful to all the honorable patrons of this webinar, respected Professor P.P. Patil, Honorable Vice Chancellor KBC NMU Jalgaon, respected Abba Sahib Suresh Patil, Honorary Secretary Vidya Vikas Mandal Sakri, respected Tai Sahib Sau Mangalatai Suresh Patil, Honorable President Vidya Vikas Mandal Sakri, Bhaiya Sahib Sri Chandrajit Patil, Honorable Vice President Vidya Vikas Mandal Sakri, respected Professor P.P. Maulikar, Professor Pro Vice Chancellor KBC NMU Jalgaon, Professor B.V. Pawar, Registrar KBC NMU Jalgaon. Without their generous blessing, it would not have been possible to organize this webinar. I am thankful to the National Advisory Committee members for giving us the valuable suggestion. I am very much thankful to Professor S.T. Bendre, Principal Dr. S.R. Jadhav, Principal Dr. E.R. Patil, Principal P.H. Pawar, Principal A.P. Kharnar sir, Principal Sharda Chitoe Madam, Dr. P.R. Sangpa for their continuous support and advice which have greatly helped us toward the successful organization of this webinar. I sincerely thank the member of the advisory committee for their valuable suggestions. I sincerely thank our guest of honor, Professor Devdatta Phase, and the resource person, Dr. R.S. Mane, Dr. Rampal Sharma, Dr. Nisha Deshpande, Dr. Prashant Sonar, for kindly accepting our invitation and gracing the inaugural function, as well as conducting wonderful sessions. I am also thankful to Principal Dr. R.S. Patil for accepting our invitation to help chief guest for the valedictory function and for guiding us. I take this opportunity to thank all members of organizing committee for their steady effort to make this webinar a successful one. I acknowledge the unwavering support received from the principal Dr. R.R. Ahire, Dr. Anand Patil, Vice Principal, all the faculty members and non-teaching staff of my college. My thanks also go all the people who have given their precious time in organizing. In particular, I would like to acknowledge and thanks to Dr. Naneshwar Chavan for managing the technical process, Dr. Sachin Nandre, Dr. Sudham Chauhan, Dr. Anup More, and Dr. Deepak Nagrale for coordinating inaugural valedictory and technical sessions. I am also thankful to all the research scholars, participants who have attended this international webinar, without whom this webinar would not be possible. I am sure that the participants must have benefited by the attending this webinar. I once again thanks everyone whose contribution has made this webinar a successful webinar. शेवटी जाताना ज्या लोकांनी राजेंद्र हिरे, पी.एच. पवार, आर.एस. पाटील, ए.पी. खैरनार सर यांनी माझ्याबद्दल जी स्तुती त्या ठिकाणी केलेली आहे. रिटायरमेंटच्या वेळेसच प्राध्यापक राजेंद्र राहिले आमचे जे प्रिन्सिपल आहेत त्यांनी या ठिकाणी हा वेबिनार माझ्यासाठी तुम्हाला ऑर्गनाइज करायचा आहे. त्यांनी माझ्याबद्दल जे काही प्रेम दाखवलेलं आहे त्याबद्दल मी सर्वांचे आभार या ठिकाणी मानतो. थँक्स टू ऑल. ओके,
धन्यवाद.
काय झालं रे? काय म्हणतोय
सर? जाधव सर,
माईक अनम्यूट करा सांगता.
माईक अनम्यूट करा जाधव.
जाधव
माईक
सर
अनम्यूट करा जाधव सर.
हो संजू दादाला अजून रिटायर नाही करायचे आपल्याला, आता आपल्याला रांगेत आणायचे.
जागा खाली कर.
सांगितलं नाराज पाटलांनी.